Right, then we have the NPN transistor biased to operate in the active mode. Two external voltages are used to establish the required bias conditions for the active mode operation. These two voltages here, however, are instantaneous voltages that change with current. Now, the DC voltage VBE causes the P-type base to be higher in potential than the N-type emitter. Therefore, the emitter base junction is forward biased. VCB, this one, causes the N-type collector to be at a higher potential than the P-type base. Therefore, the collector base junction is reverse biased. Agreed? Now, let us discuss current flow. We are only going to be talking about diffusion current components and not the drift currents, which are quite small and can be neglected. Now, look at the forward biased EBJ, the emitter base junction. Because of the forward bias, current will flow across this junction. However, it will have two components. The first one will be the electrons injected from the emitter into the base. Look at the negative polarity here. So the direction of electrons will be left to right. The second component are holes injected from the base into the emitter. Now what we usually do is that we have the first component, that is the blue line, at a much higher level than the second component, that is the red line. This can be accomplished by fabricating the device with a heavily doped emitter and a lightly doped base. So the device is going to have a high density of electrons in the emitter and a low density of holes in the base. Now the current IE, that is the current that flows across the emitter base junction, will be out of the emitter lead as shown with green arrows on the screen. This will be in the direction of the hole current and opposite to the electron current by convention. And of course, it will have the two components, blue and red. Now, most of the diffusing electrons from the emitter region are going to successfully reach the collector base junction. What I mean by successful is that a very small percentage will combine with holes in the base region and will not be able to move forward. However, since the base is very thin, this proportion is very small. So, because of this positive voltage here, the electrons are going to be swept across the collector base junction and therefore will be collected at the collector terminal. Obviously, the electrons are not collected in reality but continue flowing on into the collector terminal. The term collected is to signify that these electrons were saved from recombination in the base region. On your screen I have shown the direction of the collector current. You can also write a formula for this. IC equals IS e to the power VBE over VT. This looks familiar? Now IS is called the scale current. Why? Because it is directly proportional to the junction area, that is the device size. VT is the familiar thermal voltage and VBE is the instantaneous voltage between base and emitter, this one. Curiously, IC is independent of VCB. Now moving on to the base current. The base current has two components. The first one is shown on your screen with the red arrow. The second component is due to holes that have to be supplied by the external circuit in order to replace the holes lost from the base through the recombination process. That is the second arrow on your screen. Remember that recombination occurred when electrons were swept from the emitter region to the base region and recombined with a few holes there. These are the holes that are going to be replaced by this component of the base current. We can write IB in terms of IC as IB equals IC or beta. Now before I tell you what beta is, let me draw the direction of IB. which is of course the same as the direction of the holes it pumped into the base region. Now, coming back to beta, it is the common emitter current gain. Ideally, it is constant for a particular transistor, and its value ranges from 50 to 200. However, in reality, it does not remain constant, and so the design of circuits have to incorporate its changing value. But we are not going to concern ourselves with that right now. We are now going to write the current equation involving the collector current, the base current, and the emitter current. Since current entering the transistor must equal the current exiting the transistor, the equation is very simple. IE equals IC plus IB, that is, the emitter current is the sum of the collector and base currents. In terms of beta and IC, we can write IE equals beta plus 1 divided by beta multiplied by IC. We can introduce another parameter and say IC equals alpha IE. This alpha is the common base current gain. Alpha and beta are related to each other via these two equations. Alpha equals beta over beta plus 1, beta equals alpha divided by 1 minus alpha. Now moving on to the Pnp transistor. The biasing circuit is going to be a little bit different. Notice the reverse polarity of the DC voltages. The holes are replaced by the electrons, and the current directions of IE, IC and IB are reversed. However, all of these equations are going to hold, except that we are going to make one tiny change. Instead of VBE in the equation for IC, we are going to have VEB. Everything else will be identical.